So welcome to this pre-recording of lecture 5 on message passing. So we introduced last time the very basics of the message passing interface. The main goal of today, of this lecture, is to show that with relatively few MPI commands, you can write very useful parallel programs. So the goal is to get you started with message passing. So I will define first the important commands in C, because that allows me to carefully define what happens. But in the spirit of high-level parallel programming, I will, in the last part of this lecture, indicate how you can use message passing in Python and Julia. Algorithmically, there is the important fan out that is used in a broadcast. I will define this algorithm as well. Okay, but let's start by a simple running example that I will use to define the collective communication operations, the scatter and the gather. So what is message passing again? Well, MPI is an interface. It's actually a specification to define how one can communicate between processes on distributed memory parallel computers. Why do we use parallel computers? Well, to compute faster. And here is a very simple example, the addition of 100 numbers. Seems trivial, so you don't need a parallel computer to do this. But the addition is kind of a prototype for numerical integration. And numerical integration is used very often in scientific applications. So in a way, we are not that far off from actual applications. But the main goal of this lecture is to define how to run a parallel sum. And although we are geared towards supercomputers, this can all happen on a laptop. So we have 100 numbers given. So the 100 numbers are available at the root node at one processor. And they have to be distributed evenly among all 4 processors. So also the manager will sum. So this is an operation. We have only 4 processors. So we will also have the manager do some calculations. So every processor does the summation. So there is the distribution, and then there is the collection of the results. So this is a distributed memory computer. So every processor has in its memory a sum, and that sum needs to go to the processor with identification number 0, the root. And the root will then add the 4 sums and print the results. So if all goes well, you could have a speed up of a factor 4. So the number of arithmetical operations is decreased in this way. Okay, here is the schematic of the scattering. So we have an array of 100 numbers. The array is divided in 4 equal pieces. So this is an example of data partitioning. And the scattering is a collective communication. So every process, including the first process 0, will receive 25 numbers. This is a sequential scattering, a sequential broadcast. running ahead, this can be done more efficiently. This is already a very useful operation if you are working on a true supercomputer with thousands of nodes to test the network. So there is the communication overhead. But in this lecture, we are not talking about actual supercomputing applications. The mirror of the scatter is the gather. So after the computation, we every process has a number, so the sum of 25 numbers, and those subsums are gathered, are sent back, or are actually not sent back, are sent to the root node, to the manager node. This already indicates here that there will be, so we are working with a single program that's executed by multiple processors. Every program will have one array of 4 numbers that will be used in this gather operation. Okay, MPI defines the scatter and the gather. So here is the specification of the scatter. There are 7 or 8 arguments. The last argument is the communicator. We also have to indicate where the data originates from. That's the next to last argument, the root. And then we have 3 arguments, 3 that for the sender and 3 for the receiver. So one needs to provide a buffer, and in the more technical terminology that also corresponds to C, one needs to provide the memory location, the address where the send buffer and the receive buffer is in memory. In a higher level language, one would talk about providing the reference to the data type. So here we work always with the scatter with a composite data type. By default, you could say an array. We have to provide the count of the numbers and also the type of the numbers. Then there is the gather, which is very symmetric, so has the same type of arguments. So I specified in the previous the address, but this could also be a starting address. With contiguous chunks of memory, one can somewhere in the middle split where we start in an address. So C is also in that sense quite flexible in implementing this. So the interface is quite symmetric. So these are 2 very useful commands. And I will illustrate them now in a C program. So in a way, this lecture is self-contained. If this is your first encounter with MPI, then you have to make sure that your installation works. So we will compile with MPI CC. And that will make that the MPI.h will be recognized as part of the system. So this is the third include that we do here. There is a verbose flag, which is somehow a C-ish programming style. So it's a preprocessor statement. Not so good for longer programs, because if you would start using the integer as a variable v, or the variable v anywhere in your program, there would be some very strange error messages going on. But the preprocessor directive will replace every occurrence by v by 1. Okay, we have the initialization and the request for the processor ID. So this is the same program that is executed by every processor. So every processor can have a specific range of instructions, and what gets executed by whom is determined by this my ID. Okay, we need to declare the types. So there is this my ID, which is the processor number. We have specified at the command line the number of processors that will participate in this computation. So this is passed by this arg v, which is an array of strings provided by C. So I then have the other types. We have a counter J. We have the data, which is just a reference or a pointer to a data location, not allocated yet. We have then two arrays that are allocated. So C allows the allocation at the moment of declaration. So we have the numbers that will be summed. So every process will sum 25 numbers. So this is where the 25 comes in. And we have the sums that are gathered. So every process will have 4 numbers for the result. So there is some discipline here as a programmer. So the process with my ID will write to the proper entry in the sums. So process with ID 1 will write into sums 1. Also, this program needs to be executed with 4 processors. All right, this is again the problem, so I flipped back. Let me go now to the scattering. So the manager executes the code. So here that if statement, this is executed by the manager, by the process with identification number 0. So what does the manager do? It allocates space for 100 integers. We are assigning these integers, so the first 100 natural numbers, now starting at 1. And when the verbose flag is on, for testing purposes, we can see what these 100 numbers are. And then there is the scatter operation. So it's important, this is a blocking operation. So every processor will see this statement, but if the processor ID is not 0, it will remain blocked till processor 0 has finished executing these statements. Here is then the example. We will send 25 numbers, a scatter 25 number each, in the receive buffer to sum. So at this point it is important that at the root node, so the 0 here, the next to last argument, that at the root node there are 100 numbers available. So the 100 is never here, but we are running this with 4 processors. 25 integers will arrive in the receive buffer to sum. Okay, then as a check, we can print, so every node can print out 25 numbers. It may now be that this output is completely garbled if there is not much buffering happening. And then there is the summation. So there is no guard, there is no if my ID is this or that. So every process will execute the summation. So but you can see here, every process writes in a separate location. So process with ID 2 will write in the sums that are indexed by 2. So there is this plain sum, and then there is the other communication. So we pass the starting address. We pass the starting address where we gather. So here we gather only one element, it's one integer, and it's gathered into sums. So the next to last index here is the identification number of the receiver, which is here the root node. Perhaps I can flip briefly back and forth. So here is the corresponding picture. So this is what happened. We have our sums. So every process has this array of 4 numbers, and they are gathered at the root node. Okay, and then there is the end. So the end is where the 4 sums are being added up. And the nice thing about this problem is that there is an exact answer, so you can print out what the sum should be. Okay, so this is a parallel summation in C. We can, and this is defined with collective communication, with the scatter and the gather. There is also the point-to-point communication. I will illustrate the point-to-point communication with another problem, but the one exercise is to redefine the parallel sum, but now with the send and the receive operations. So in a way, so I'm more than 15 minutes in this lecture. In some sense, if you really want to condense it, if you know the send and the receive, these are very primitive operations, but with that you can define many useful operations. So after this lecture, we can already do some write some very useful programs. Okay, what is the problem? So I mentioned numerical integration. What we will do when we do numerical integration, we will evaluate functions. So here we will just square the numbers. So we have some numbers to square, and that's only one multiplication, but you could imagine that this is a very difficult, complicated function to evaluate, which would involve the running of another program. But now we can have the different processors running that difficult function. So the data that is needed to be squared is at the root node. So the root node will distribute the numbers, and the amount of numbers that will be squared will be equal to the number of processors. And also the root node will square one number, will square the first number. But here you see the run at the command prompt. So the program computes the numbers that needed to be squared, and every node actually prints out the received number and then returns the number that was squared. So this is also a scatter and a gather, but we will do this now with point-to-point communications. For clarity, so here is the parallel squaring algorithm, or the parallel evaluation of a function on different data. So in the classification of Flynn, we had the same sequence of instructions, or different instructions if there are different functions, but executed on different data. So with the parallel squaring, we have the same instruction but on multiple data. So this would also be a great, and we may retake this when we get to graphics processing units. Okay, here is the algorithm written in plain sentences in sequence. There is the sending, the receiving. There is the computation, and then there is again the sending and the receiving. Notice the mirroring. So the manager sends, does p minus 1 sends. Every worker, so there are p minus 1 workers, every worker receives. So there is an explicit loop, but there is also an implicit loop happening here because the same program is executed p times. There is a nice symmetry. So there is one send statement that every worker does, but then the manager does again a loop for the matching receives. So what is important here, point-to-point communication is much more flexible, but the programmer must be much more disciplined that for every send there is a matching receive. Otherwise, the program is blocked. All right, so here are the specifications. So the send starts with a buffer. You can send one number, as we will do, but you can also send an entire array of numbers. You must specify the data type. There is a destination, and then there is a message tag. The message tag, the message tag is in some sense not strictly necessary, but it helps you to label. So the send message tag should correspond to the receive message tag. This allows for visual inspection of the code that every send has a matching receive. The receive has similar. So we are receiving from a source now. The first three types are the address for the receive buffer. In a language such as C, the programmer must have allocated memory. In languages such as Julia or Python, this is typically taken care of. Although you sometimes may have to declare an array that has also that number of elements that you want to use. C still has the advantage that you must be very explicit about memory allocations. With high-level languages, it often is hidden, but when something goes wrong, it is harder to find out what went wrong. Here we have a status object as the last parameter. We will not use this here, but later on we will see non-blocking communications, and there the status will be important. Okay, here is the start of the C program. I will point at the declarations, so the programs no longer fit on one slide, but breaking it up in slides has still the advantage that I can point at the code that is actually copied, also the initialization, the getting of the size, getting of the rank. This is code that always is copied. I will point at the names of the variables. So we have P and my ID, the number of processors. The P corresponds here with the P that was introduced in the pseudocode of the algorithm. We have the counter I, the function value, and then also the star x, which will be used as the address for the communications. So here I am doing the explicit allocation. So we allocate the numbers that need to be squared. So there are p numbers that need to be squared. So here the allocation is done by the manager. Only the manager has to know all the numbers. And the manager has the number 2 for itself, and we square the multiples of 2, 2, 4, 8, etc. Then for debugging purposes, we print the numbers. Okay, now is the critical portion here. You see, the programs are still elementary enough so that everything fits on one slide without having to shrink dramatically. So there is an implicit loop. The single program, this if-else statement, is executed by all processors. So you see an explicit loop. The manager will do all the send operations, thus p minus 1 send operations in the if statement, in the if block. In the else block, there is a loop as well. So there are p minus 1 matching receives. So it's important that we can verify the correctness of this communication. So for every matching send, there is a matching receive. For every send, there is a matching receive. For every receive, there is a matching send. So if you have to reason about the correctness, you have to refer to the single program multiple processors model. So there are p processors executing this this program. So, and even with the debugging, so there is even the extra print. Every processor, when the debugging flag is, the verbose flag is on, it will write the numbers in an interactive environment. Okay, so then the actual computation, which is f star equals f, so that's the syntax in C to do the squaring. So the number f is replaced by its square. This could be simply replaced by a function call. And also here, every function could have its, every process could have its separate function. So the data is different. So every processor has a different f. Then there is again the critical communication. So there is the receive that's happening by the manager. So the manager executes p minus 1 receives, and every worker does a send. So there are also p minus 1 send operations, even though it's not obvious if you just look at the code. So again, this is the single program executed by multiple processors. So it takes a while to get used to this reasoning, but once you get the logic, and I will also illustrate this in Python and Julia later, then it seems rather natural and very useful as well. So that's the whole point. Okay, the end, the finalize. So the manager prints the squared numbers. So this is an interactive parallel program. If you run this, so don't go overboard with the number of processors. These are simple interactive programs. It may be that you have only 4 cores that you can run, but 4 cores is sufficient to test this out. Okay, but nevertheless, this is already very useful when we go to an actual supercomputer in the middle part of this course. You can test this. So in a real supercomputer, you have to submit a program for batch execution. Whenever the resources are free, your program is launched. So then the simple interaction will no longer work at the command line. So at the command line on a Linux-like system, we do this with time, or on Windows with measure command. That no longer works, but there is the MPI W time, so that will give you the wall clock time. So the programs that we are seeing in this lecture are already very useful to measure the total communication cost. So even that program of the squaring, you could run on thousands of processors. Perhaps you have to be careful about the overflow with the doubling of the numbers, but that's just a detail easy to fix. But this would already be useful to check how much time it actually takes to do this, and because the communication overhead will dominate here. We only do one multiplication. Okay, we have seen a sequential algorithm. I would think and hope even that if you are using the built-in scatter and gather implementations, so the MPI defines only the specification. So then there are the specific implementations. So OpenMPI is one of them. I would hope that the scatter is here shown in 2 ways. So there is the sequential broadcast where processor 0 sends first to itself, then send to 1, send to 2, 3, 4, 5, 6, 7. So with 8 processors, you see this will take 8 time units. So this is a sequential broadcast, but if you think about this, you can actually do much more, much better. So as soon as process 1 has its number or its data, it can also participate in the sending. So it can participate in sending to process 3, while process 0 sends to 2 in the second time step. So at that moment, already 4 processors have all the data, and they can send to the remaining 4 processors. So this is a fan-out broadcast. So with this picture, you can see the name. It's also the definition of an algorithm. So instead of having 8 time steps, you can do this in 3. And 3 is the logarithm, the 2 logarithm of 8, or 8 is 2 to the power 3. Does not make much of a difference with 8 processors, but if you work with 1024 processors, it will reduce this in 10 steps instead of 1000. So that is a speed up of 100. If you work with 1 million, so that's 2 to the power 20, you will do this in 20 steps instead of 1 million steps. So logarithmic is always logarithmic, cost is almost constant cost. So this is why the choice of the algorithms matters here a lot. So often people have the misconception if you work on a very powerful computer, you can be a bit lax with the algorithms that you're using. The opposite is true. So if you work with 1 million processors, you better use a fan-out broadcast. Okay, so here is the algorithm. So the algorithm, we will, so it's also an exercise to actually to define this with MPI. The algorithm is defined here. So we have the source and the destination. So processor J sends to J plus a power of 2. And the corresponding processor receives. So then for a sequential broadcast, the cost is proportional to the number of processors. So the big O means that it's up to P, depending on some constant. With the fan-out broadcast, we can do the logarithmic costs. So I've shown the picture for a fan-out, but you can also have a fan-in. So I should have changed this here in a fan-in broadcast. So the mirror can also be done. So one should essentially also implement the scatter in a more efficient way. So this is the main algorithm that we see today. These efficient communications, collective communications. Okay, we will come back to that later. So in the last 5 minutes, I will indicate how to do this with Python and Julia. So Python has the send and the receive. So the advantage of Python is that the syntax is a lot more condensed. So you have only 3 arguments. The other advantage is that any Python object can be sent and received. So Python also essentially allows to declare explicitly. But I will first show the sending and the receiving of dictionary. So here the slide is very self-contained. So we have the bottom 3 lines on the execution. Only 2 processors will take part in this. So we have the root processor that will define the dictionary and send the dictionary. The destination is 1, so the other processor here will receive and print. So this is a very simple send and receive. There are also wrappers for the scatter and the gather. So here you see the parallel sum. This was done on 10 processors. So if you work on a laptop with 4 cores or 2 cores but 4 with hyperthreading, then do this only for 4. I executed this on multi-core machine. So this is the parallel sum that will use a numpy array. So I mentioned the declaration of types, but as soon as you start using numpy, you are typically using typed data structures. So in a way, the fact that you are working with numpy arrays already makes that you work with contiguous blocks of memory. which is always better than just linked lists. And that also you worked with arrays where every element has the same type. So in a way, Python is high level, but Python is not always very slow if you start using NumPy, which executes compiled code, by the way, on um, arrays. So here you see the working with typed data. There is something subtle, perhaps a little bit too subtle. Python is case sensitive. There is a send with a little s and a send with a capital S. The capital S is strongly typed, so you must provide the type. So here we actually specify that we're using MPI integers. So we are slicing the data. So this can be executed by any number, although I fixed the n to 10. This can be fixed. So yes, it's executed by, I made sure that the slices had dimension 10. So every slice will be consisting out of 10 numbers. So you will be summing more numbers if the number of processors increases. Notice the important part of this lecture was too that for every send there must be a matching receive. So there is still, so now actually the virtue of Python is that everything is on one slide. So the initialization, declaration, getting number of processors, getting the process ID, the for loop of the send, the explicit for loop, and then the implicit receive. So source and destination are defined. And actually the program is here defining the scattering. So then we have the gathering. So I was lying when I said that everything fits in one slide. So you have the calling of a function. So the summation here is the summation that will work on numpy arrays. So it's not the Python sum. There is here also the explicit declaration of space for all the sums. If you do the gathering, then there is actually a sums where size is the number of processors. So there is one send apparently, but this program is executed by every processor with rank larger than 0. So the manager node will not execute this send statement. So we have size minus 1 many sends. And this is mirrored by the explicit for loop starting at 1 and going to size minus 1. So where you have the matching receives. So again, the important aspect of this lecture, how do you prevent, this is blocking communications, how do you prevent that these communications block your entire program? Well, be careful to make sure that every send has a matching receive, every receive has a matching send. Okay, so then my last slide is Julia. So I could repeat everything with Julia again, but this is a graduate course. I expect some versatility. Everything is also documented. I'm also relatively new to Julia. MPI is only the MPI wrappers for Julia only a couple of years out. But it's easy to use. So here you see the Julia syntax. The disadvantage of mingling Julia with Python is that when you write Julia if else statements that you forget the end. but other than that, I want to emphasize the same high level aspect here. So Julia also has dictionaries. If we want to send a dictionary, so this is a program for two processors, then we can do this. So the high level dictionaries are possible. This is not to say that with MPI you couldn't be doing this, but defining structures in C is more elaborate. So with this lecture, so this is towards the end, I hope that I have given a good impression on what can be done with message passing. So essentially, with about five or not more than 10 MPI commands, you can already get started with defining very useful parallel programs that will run on distributed memory parallel computers. Rather than working in one language and covering everything, in this course, we will kind of work with three languages. We have the multi-language approach, where you can fill in the blanks. So summarizing, uh, I like to focus on a hands-on approach. So the programs that I show, they work. They have been tested on multiple platforms, but there is also the algorithmic aspect. So there is the fan out broadcast and the fan out scatter and the fan in gather operations. You will get most out of it. So there is the theoretical aspect. So we have introduced a hypercube network topology. Uh, and there the processor nodes are actually typically represented in their binary expansion, where two processors are connected if their binary expansion of their network ID differs with one bit. So there is a theoretical aspect in this course, show that with a hypercube network topology, you can actually efficiently implement the fan out broadcast. So that with P processors, the cost of a scatter is logarithmic, quasi constant in the number of processors. So Julia's recently. If you don't know C, then this is also an invitation to C. So I try to be quite explicit when I define C programs. C is still the least common denominator. One may disregard this, but all languages interface with C. So if you understand C, then you can build a Python wrapper or a Julia wrapper. And both Python and Julia are also ubiquitous and very easy to use. So this is not a programming course, but I hope that with very small programs, you can essentially define how parallel computations work. So I hope this recording was interesting, and I thank you for watching.